Video 3, we are going to continue our endeavor with slopes and some other stuff to really get involved in identifying quadrilaterals purely based on their coordinates. So in the last video we talked about what if we already knew the lengths of each side and what if we already knew the slopes of each side? How could we use those values to determine what quadrilateral specifically must we really have here? Well, now we're going to regress a step back and say, well, what if I only gave you the coordinates and I still want to know what type of shape this is? So we're going to look at one of two types of questions. Number one, I'm going to give you coordinates and I'm going to tell you what shape it is, but you have to prove to me that it really is that shape. So you have to use the properties of that shape to verify that yes, those properties are there and thus it is the shape you say it is. The other type of problem I will give you is I'll just give you 4 coordinates and I'm not going to tell you what type of shape it is. And you have to determine based on the lengths and the slopes that you have to make that final determination that it must be this specific quadrilateral. So in this particular example, I'm telling you that we've got a square. Okay? And I've even graphed this to give you an idea of what we're looking at. We're kind of looking at a rotated square. It looks like a square. Can we say that it's definitely a square? Not just by its looks. So we need to think about, well, what properties make a square unique? Well, squares have 4 right angles and 4 congruent sides. Okay? No other quadrilateral has both of those things. Now, how are we going to prove that there are really 4 right angles and 4 congruent sides? Well, to prove there are 4 right angles, we would need to see adjacent slopes that are perpendicular, because those would make our 90-degree angles, and we would need to see congruent side lengths. Okay, so let's talk about how we're actually going to accomplish that now. And we're just going to use stuff that we've used in the past. Not necessarily this year, but maybe somewhat last year in Algebra 1. So we're going to use the distance formula, and we'll talk about an alternative to the distance formula that we have used previously this year to calculate our side lengths. Okay, if we want to know the length between each set of points, that's going to give us the length of our sides. And there's 2 ways we're going to use the slope formula. We can use the slope formula to see if opposite sides are parallel, right? If we have a trapezoid or maybe a parallelogram or neither. And we can also use the slope formula to see if we have adjacent sides that are perpendicular, thus giving us 90-degree angles. So here's the distance formula. And again, we'll talk about an alternative that I thought was maybe a little easier to use than the distance formula. And we've got slope from back in the day in Algebra 1, which was just y minus y over x minus x. Now, with the distance formula, if you remember this was really early on in the year, in school year, we talked about how the Pythagorean theorem could really be used in place of the distance formula, okay? And all we did to make the distance formula look like the Pythagorean theorem was we just subtracted our coordinates. We kind of stacked our coordinates of our 2 points on top of each other, so the x's and the y's were right above and below each other, and we subtracted them. We always subtracted. And the 2 numbers that we ended up with here, these 2 differences, were the a and the b of the Pythagorean theorem. So then you could just take these 2 numbers and go a squared plus b squared, and the number we were trying to figure out was always going to represent the hypotenuse, which is always the c side. So c is what we were really trying to figure out in the end. So you would know what numbers a squared plus b squared would actually add to b, then we would have to take the square root of both sides to figure out what the actual length of the distance between a and b really was. So if you look at my picture here, x1 and x2, like let's say this is x1 and this is x2, and if we subtract those values, the distance in between really represents this horizontal part of the triangle that we could make between these 2 points here. Okay, AB is the main thing we're concerned about. We really want to know how long this is. But between every 2 points, we can always end up making a right triangle out of it using natural vertical and horizontal lines. So the difference between the 2 x's gives us our horizontal piece, and the difference between the 2 y's gives us our vertical piece here, which is always naturally going to be, again, your a and b for the Pythagorean theorem. Now, for slopes, what you'll notice here, and I'll point this out, especially when we actually do some examples here, is the slope formula, which is y minus y over x minus x. So we're subtracting the y's and we're subtracting the x's. Well, isn't that what we're doing over here if we're doing kind of the Pythagorean theorem / distance formula? So what we'll discuss is really we can use these numbers not only for the Pythagorean theorem, but also for our slope if you really think about it, right? So let me just take a quick pick here. And pop it over here. So if we need to subtract our y's, that's what we were doing right here, and that number that we got was b. So we can think of the slope as the b number, and when we subtract our x's, that's when we got the a number for the Pythagorean theorem. So the a and the b of the Pythagorean theorem, which are really the difference of the x's and the y's, can be looked at as just b over a, and that's our slope, which we may or may not have to simplify, FYI. All right, so equal slopes meant we had parallel lines, and negative reciprocal slopes meant that we had perpendicular lines, which meant we had 90-degree angles. So we would need to have that for our, definitely for our rectangles and for our squares. So let's go back to the square. Notice I don't have the graph anymore. I don't really need it, but here's what we're going to do here. The first thing I would do is I line up all of my points in sets. So I know A and B are connected together, so I write the coordinates for A, and then I write the coordinates for B underneath. So I'm going to set myself up to do the subtracting here to get the A and the B values that I need. That will work not only for the Pythagorean theorem, but also for the slope. And then B and C are connected. And so I'm going to set that up to subtract. And then C with D are connected. And then last but not least, D is going to connect over back to A. All right, so now let me do all my subtracting here. And this is the one part where people make silly mistakes because they forget about a negative sign or something like that. So 6 minus 10, that's negative 4. 9 minus 6 is 3. 10 minus 7 is 3. 6 minus 2 is 4. 7 minus 3 is 4. 2 minus 5 is negative 3. 3 minus 6 is negative 3, and 5 minus 9 is negative 4. Again, all four of these sets represent different triangles for the Pythagorean theorem, and each one of those numbers represents the a and the b value. Well, if you notice, if we have to do a squared plus b squared equals c squared, and these represent a and b, even if we have a negative number and we square it, that means we're really going to take a negative times a negative, which means it's a positive. So we had mentioned before, in terms of length, the negatives truly don't matter. I wouldn't chop them off right now because the negatives will matter with the slopes. Okay, but just keep in mind, whenever you square this negative 4, you're really going to get a positive 16 out of it. Well, if you notice, if the negatives really don't matter in terms of the Pythagorean theorem, notice all four sets of these have 3's and 4's. And so this was one of our special Pythagorean triples where the hypotenuse was going to be 5. Okay? So, wrong button. Here's what we could do next. I'm just going to move this up out of the way, get some extra space here. So now I can say the distance of AB would be 4 squared plus 3 squared. And I'm just going to put, I already know what that is. It's got to be 5, right? So then the distance of BC, again, I'm just going to write out how I would set it up. In this case, again, I know that's going to end up being 5. The distance of CD is the square root of 4 squared plus 3 squared. Notice I'm just chopping off those negatives with the distance because I can't really have negative distances in there. And then DA or AD really doesn't matter which. And again, I'm going to chop off those negatives, and I get 5. Okay, so what I'm going to do now is pull all these together and say all 4 sides are congruent. And that satisfied the first part of this really being a square. It's got 4 congruent sides. Now you might go, can we just stop right there? This must be a square because it's got 4 congruent sides. No, because it still could be a rhombus. It doesn't have to have, rhombuses don't have to have 90-degree angles, so maybe this is a rhombus. Now we got to explore the slopes. So I'm going to take this, shrink it down just a little bit so I can get some space in here, and then let's talk about the slopes. All right, now if we grab our slopes here, slope is m, so we'll say m sub AB, so the slope of side AB. All we have to do is take our second number, which was our y minus y, right? And then our a number, the -4, which was our x minus x. Now, all I'm going to do is just pull the negative out front, just so it doesn't get tricky like, well, does the negative go on the bottom? Does it always go on the bottom? The negative could technically go on top, but it's only there one time. You can't have -3 over -4, because then technically it'd be positive. And if you can simplify, I would definitely recommend simplifying your fractions. So BC, the second number is 4, first number is 3, and that doesn't simplify at all, right? And it's still positive. You can rewrite this if you want. You really don't have to. You know, I could just leave it as that if I really wanted to. If I understand that this is truly negative, then the slope of CD is going to be -3 over 4. And the slope of DA or AD, really doesn't matter, is -4 over -3. Now here, I'm just going to cross those out. So this is really +4 over +3. Now what I want to look at are the opposite sides. The opposite sides would be AB with CD. That would be one set of opposite sides. The other set of opposite sides would be BC with DA. And what do I notice about those slopes? Is 3 over -4 the same as -3 over 4? Yes, those sides are parallel. Is 4 over 3 the same as -4 over -3? Yes, those sides are parallel. Now, that satisfies the requirement that a square is a parallelogram. The opposite sides are, so I'll just clump those together. We'll say both sets of opposite sides are parallel. So we've met that condition. We still got to show that there are 90-degree angles, and to do that, we need to look for adjacent slopes that are perpendicular. So I'm going to scooch this over a little bit and write on the left side of all this. So these would be adjacent slopes, A, B, and BC. And is -3/4 and +4/3 negative reciprocals of each other? And the answer would be yes, they are. So those are perpendicular. Now, does that mean you can just stop right there and say, yeah, we got one 90-degree angle, so all of them are 90? It depends on what other properties you know, but we're just going to keep going, okay? So BC and CD, we look at those slopes. 4/3 and -3/4. Yes, those are negative reciprocals. Those are perpendicular. CD and DA, those are perpendicular. And our last set of adjacent slopes would be all the way around here. Those last two slopes, sorry for that interruption by the principal there, they are negative reciprocals, so they are perpendicular. So now I've got 4 sets of adjacent perpendicular slopes, therefore all 4 angles are right angles. And that meets finally our third, if you will, condition for being a square. The main two things I had mentioned earlier were that we had to show it had 4 congruent sides and it had 4 right angles. Technically, the other partial definition of a square is that it is a parallelogram, which I also satisfied right here. So slopes, there's always 2 things to be on the lookout for: equal slopes for parallel sides and negative reciprocal slopes for right angles. Then you're only really using your distances one time just to determine if there are congruent sides or not. So that is to prove that a square really truly is a square. Now, we're going to do one more problem together. Here's the second problem. We have our 4 coordinates, and all I've said is that it's a special quadrilateral. We don't know what kind it is. We're going to have to prove that it is some sort of special quadrilateral. So we're going to need lengths. We're going to need all 4 lengths, and we're going to have to look at all 4 slopes. And again, remember, the slopes are going to tell us one of 2 things: either that we have parallel sides or we have perpendicular sides giving us 90-degree angles. So likewise with the first example, I'm going to set up my points and stack them on top of each other in sets. So J and K are going to be right next to each other. So I'll set those points up. And then K and L will be next to each other. And then L and M will be next to each other. And finally, M is going to wrap around back to J. Okay, and then we said for each of these, we're going to subtract our coordinates so that we can get our A and our B for our Pythagorean theorem, and technically also our rise and our run for our slopes. So 16 minus 19 is negative 3, 3 minus 0 is 3, 19 minus 16 is 3, 0 minus negative 2 is positive 2, 16 minus 13 is 3, negative 2 minus nothing is still negative 2, 13 minus 16 is negative 3, and 0 minus 3 is negative 3. So if I'm scanning through here, again, these are going to be A and B for a Pythagorean theorem, another Pythagorean theorem, another Pythagorean theorem. The first thing I notice is not all of these sets of numbers are exactly the same, even if you reverse the order of them. I notice that these two are the same, and I notice that these two are the same. And I notice that they aren't opposite of each other, that these are adjacent to one another, and these are adjacent to each other. So I think I'm going to end up with two pair of adjacent congruent sides where it doesn't look like that either opposite set of sides are going to be congruent. So my first inkling is that this is going to be a kite. But first I need to also show that necessarily that none of the sides are parallel. So if I were to start setting up and getting my exact side values, okay, just looking at the A's and B's can give you an idea of what the distances will be, but you still have to complete it. So the distance of JK, the distance of KL, the distance of LM, and the distance of MJ. So we're going to set up our 4 Pythagorean theorems here. So the square root of, first one here, again, we can ignore the negative with the distances. So 3 squared plus 3 squared. Well, let's see, that's going to be 9 and 9, which is 18. And the square root of 18, ooh, I get to simplify this. That's the square root of 9, the square root of 2. So this is really 3 root 2 simplified. Now, do you have to simplify? I guess not really. So you could just leave it as the square root of 18 and call it a day with that. I don't think it's going to hurt to leave things unsimplified by any means. Second one, we'll have 3 squared plus 2 squared. So we'll have 9 plus 4 is the square root of 13. And then we'll have 3 squared and another 2 squared. So again, we'll have the square root of 13. And last but not least, we can ignore the negatives with distances. So we have 3 squared and 3 squared, which is another square root of 18. So if I'm looking at this, again, I've got these are congruent adjacent sides. It doesn't really look like they're adjacent, but remember the beginning and the end sides here are really adjacent to one another. And these two sides are congruent and they are adjacent. So this is looking like, yes, it might be a kite, but we also need to verify once again with our slopes. So let's do one more little step here. Let me shrink that up, kind of move it out of the way. So now the slopes. The slope of JK, the slope of KL, the slope of LM, the slope of MJ or JM, it doesn't really matter. So again, for the slopes we said we're just going to take the B number up here, which is technically the y minus y, over the x minus x, which is our A, which is negative 3. Okay, I'm going to go ahead and simplify that, and that's really negative 1 over 1, or just negative 1 if you wanted to. But I'm going to leave it as a fraction, because sometimes if you don't leave it as a fraction, you don't get to see the reciprocal action in play. KL is just going to be 2/3, and that's fully simplified. LM is going to be negative 2/3, which is fully simplified. And MJ is negative 3 over negative 3, which is positive 1 over 1. Again, I'm just going to leave it as that 1 over 1. I could just say 1, but I'm not. Now, are there any equal slopes amongst our 4 slope values here? And no, we almost have some equal slopes, right? 2/3 and negative 2/3 almost, negative 1 over 1 and positive 1 over 1 almost. So we could clump these together and say no parallel sides. And so if we have, up here, we had two sets of adjacent congruent sides with no opposite sides congruent, plus no parallel sides equals, this has got to be a good old kite. So again, you're going to use your numbers here to make a claim about what's true about the sides, if they're all congruent, if some of them are congruent, or none of them are congruent really. And we're also going to use our slopes in one of two ways. Now, notice I didn't talk about perpendicular stuff here. If I thought this was going to be a kite, kites really don't have to have perpendicular sides and have 90-degree angles. They could, but it really doesn't matter. I just wanted to verify that there were no parallel sides, and there weren't. So I just left it at that. Now, if you were in a tie between, let's say, a parallelogram and a rectangle, you would need to show that if certain sides were perpendicular and thus giving you 90-degree angles. Now, the last problem I want you guys to try and bring to class, and we'll go over it. So you must have taken all the notes, and you need to do this problem on your own and try it out. Okay? At least attempt to try it out. Give it a good try. And that's all for video 3.